Hello, welcome to another video. This one we're going to talk about decay series. Now, we've seen a version of this figure elsewhere, but not exactly this one. So let's have a look at it before we try and talk about it. Make sure that we know where we are in this graph. What we have on the horizontal axis is the number of neutrons, and what we have on this axis is the number of protons. So we're moving through the elements as we go up this scale here, starting with hydrogen, helium, getting the heavier elements, carbon, so on. And this is the number of neutrons. So it's a little bit different from what we've seen before, but it's similar. And these symbols represent all the isotopes that occur at various numbers of protons and neutrons. Now the stable nuclei are represented by the black dots. Now, what's the definition of a stable nuclei? Well, all sorts of things, but basically one that has a very long half-life. And when we talk about half-life, that will make a bit more sense. Basically, it's not going to decay. Doesn't say that it can't, but it's not going to. The squares represent beta decay, so these isotopes are less stable, so they're more likely to undergo beta decay, and these guys, the triangles, are not stable either, and they're likely to undergo positron decay. And so you can see there's a sort of band of stability around which all the unstable isotopes hover. Another representation of this is, again, let's zoom in on a bit of that diagram, but we're not only zooming in, we're not only making it colour, we're flipping the axes. So this is neutrons and this is protons. And so here we're in the heavier elements. And what we're trying to show here is the black ones are still stable. The blue ones are beta emitters. The red ones are alpha emitters. And the yellow ones are electron capture, which we don't need to know about. Or positron emitters. We also don't need to know about. But what they're trying to show here is, and I'm going to reinforce it, is that atoms do not stay the same element in their lifetimes. They can actually move from being one element to another element depending on what sort of decay they undergo. And it's fairly systematic. Going from here, some atoms can go jumps across like that. If you undergo alpha decay, you do a jump like this. And so you start off here, they started off with 62 protons. They emit an alpha particle, so you lose those 2 protons and you become 60. And so what they're trying to show here is it's actually jumped down 2 neutrons as well. So there's a total change of 4, and that's why it's like that. Whereas a beta emitter goes in this direction. And so atoms can actually move around, they can hit a stable one and sit there for quite some time, or they can keep moving. And that's what we call a decay series, is when an atom undergoes a chain or a sequence of radioactive decays. And so it can be a combination of alpha, beta and gamma. Could just be alpha, could just be beta, could be a mixture. There's a whole lot of different decay series that occur. But basically they gradually change and become lighter, and ultimately they aim to become more stable, because these atoms are decaying because they're unstable, and eventually they'll hit a stable element and they'll stay there. This is pretty much saying the same thing again. Quickly scan that. Should have popped that up earlier. So we're going to flip the axes again and have slightly different ones as well, just to confuse you. Here's our atomic number, so our elements are along here, but this case we have mass number, so that tells us that protons plus neutrons. And here is a decay series. Beta positive decay causes a jump like that. Beta negative decay causes a jump like that. So that's the beta that we normally talk about. And you can see on this diagram that most of the beta decays are beta negative. And then alpha causes a jump like this, because you're losing an alpha particle. So here they start off in this decay series with uranium-238, might be a bit small to see, but that's uranium-238, undergoes an alpha to thorium, then a beta, then a beta, then an alpha, then an alpha, then an alpha, then an alpha. Then it comes to here, which can decay either beta or alpha again. And then you have this that gets polonium, then it gets to lead, and then eventually, no matter which pathway they took, it ends up with a stable isotope called uranium-206. And that would be a decay series. Quite an elaborate one. And that could take each of these jumps. Some of these jumps represent different periods of time. And when we do half-lives, we'll talk about that a little bit more. Some of them may be almost instantaneous. So when you get here, it jumps automatically there by emitting an alpha particle. Sometimes it might sit here for thousands, potentially thousands and thousands of years until it decays. Now, you need to do some practice, and so what you're going to do is a decay series. Similar to the ones we've done before, what you have to do is fill in the numbers. I'm going to just do the first part, and so, whoops, uranium. What's uranium? Let's go back. I need to go back one to find out what uranium is. Whoops. Uranium is 92. There you go. I can remember lots, but I can't remember everything. What was it again? 92. So I write 92 there, and here we've got 2, so 2 plus something equals 92, so that's going to be 90. This is going to be 230 plus 4 equals 234. So I'm not certain what 90 is. I should have done my research before. But what you do with this symbol here, whatever you work out, you move it down to here, because we're just showing a decay series. This arrow, all it's saying is move this symbol down to here. So we can put a 90 there, we can put a 230 there, and we can put whatever we've got there. And then we do the next step, recognizing that this one will of course be alpha, and so forth. So that's how you do, and this sheet keeps going. So you can do that in class, and I can give you a hand with it if you have any problems. And I think, let's do an example. We've got another example, and showing a decay series, but in this case we're causing a decay. And so I want to show how to just interpret this word. So here we have a word nuclear equation. We need to translate it into a nuclear equation. And a couple of things. We should just use a highlighter. Have we got a highlighter? Does it highlight? No, it doesn't. We got bombarded. So that means we're hitting it with alpha particles. Okay. And that means the alpha particles are there at the beginning, the before and the after. So when we do our nuclear equation, we have before and after the event. And you have to sometimes read these word ones carefully to determine what you have before and what you have after. And so clearly we must have the beryllium 9 and 4, but because it's being bombarded by that, they're already existing, so they have to actually go here, and we put in the symbol for the alpha particle. What else are we told? To form a new isotope. Well, let's put in our clues to what the new isotope might be. You don't have to do this, but I do it just to help you. And a neutron. And if we go way back to where we had a table of symbols, the neutron is given by a little n. Now, this number is the number of protons, and there's no protons in a neutron. So that's 0, but it weighs 1. So we have a 1 there. So you can actually work it out if you've remembered enough things. And we need to fill in the numbers and the symbol. Alright, so let's see, 4 plus 2 equals 6, something plus 0 equals 6, so that's going to be 6. Now I do remember that element 6 is carbon, but you've got a periodic table, you don't have to memorize that. This side, 9 plus 4 equals 13, 13, something plus 1, so that's going to be 12. So this isotope is carbon 12. That's your answer. Now what I'll do is I'll get rid of that, and I'll bring it up, the model answer that they've gone through. There you go. Now you should pause this and have a read of it, because they do it a similar but different way. They do the whole steps, and make sure you understand what they've done. Unless of course you understand what I did, in which case you can just keep listening. Notice down here though they've got a typo. They've got the 6 on the wrong side. That happens. And you should be able to do all those questions in your booklet now. Fantastic. And question 3, is there any tricks? This one is a word one. You just got to read it carefully and identify which side goes with which. You should be able to do that one okay. Uranium is hit by a neutron. Remember the symbol for neutron. Element X is bombarded. Now X means that we don't know what it is. So you're given enough information to work out what element X is. And this is your unknown in this case is going to be on the left hand side of your equation. That's the only trick to that one. Bismuth. Alright, now this one is a little mini decay series, so you've got to write 2 equations, and here you've just got to write the alternative equation, 2 equations for it. That's not too bad. In the next video we're going to revisit ionizing power and penetrating power. We'll talk about that as well. Cheerio!